So for this first problem, we want to come up with a graph. The first thing we're going to do is look for vertical asymptotes or horizontal asymptotes. So for vertical asymptotes, I'm looking in the denominator. I need division by 0. And we do get division by 0 if x equals positive or negative 2. So I'm just going to start making a little inventory of stuff here. Vertical asymptotes when x equals plus or minus 2. For horizontal asymptotes, in order for there to be a horizontal asymptote, the degree of the numerator needs to be less than or equal to the degree of the denominator. And in this case, the degree of the numerator and the denominator are the same. So in that case, we take the leading coefficients of the numerator and the denominator and divide them out. When we do that, we have 2 divided by 1, which is just 2. So we have a horizontal asymptote at y equals 2. There are no slant asymptotes here because the degree of the numerator is not exactly 1 more than the degree of the denominator. Plus, we already have a horizontal asymptote. So let's get those asymptotes drawn in here as dotted lines, and that will begin to form our picture of the graph. I like to graph things as I find them because it starts to form the picture for me in my mind. And there we are. So we know that the function, as it goes off, as x gets infinitely negative or infinitely positive, the function will start to tend towards the horizontal asymptote. As it approaches these asymptotes from both directions, the function will tend to go off to either positive or negative infinity in both cases. So we already have a pretty decent idea of what this thing is going to look like, hopefully. The next thing we need to do is figure out where the y-intercept is and where the x-intercept is, or intercepts if there are any. So for the y-intercept, we set the equation, we set x in the equation equal to 0. So for, let me see some space here, y-intercept, we would have basically y equals, x becomes 0, so that's 2 times negative 9 divided by 0 minus 4, which is negative 4. So that would simplify down to negative 18 divided by negative 4, which reduces down to 0, comma, positive 9/2. So I can mark that on my graph now, 0, 9/2, that's 4.5. So 1, 2, 3, 4.5. Right there is my y-intercept. For x-intercepts, we need to set y equal to 0. So this time we'll have 0, I'll label it x-intercept, just so that I know what I'm doing. Set y equal to 0 here, so we have 0 equals 2 times x squared minus 9 divided by x squared minus 4. And now we multiply both sides by the denominator disappears. I can also divide both sides by 2, and that 2 up front disappears. And then I'm going to reverse the way this is written. X squared minus 9 equals 0. So now we just solve for x. We have x squared equals 9. Take the square root of both sides. X equals plus or minus 3. So over here I have x-intercepts of 3, 0 and negative 3, 0. So I'm just keeping a little inventory of all the stuff that I've found so far. So I can mark those on my graph. I have those 2 points now as well. So with that in mind, and knowing that we're going to go off towards these horizontal asymptotes here, and because I'm approaching an asymptote here, I'm kind of guessing that my graph is going to do something like this and something like this. I don't really know what's going on in between though yet. And that's just a guess. We don't want to do anything with that just yet. So okay, let's see. We have y-intercept, we have x-intercepts. We have our asymptotes marked down if we need them. So let me go back to the steps, and we've done this, we've done this, we've done this. Okay, so now we need to start looking at the derivatives. I've already given you the first and second derivative here just to save time. So to find the critical numbers of the first derivative, we set it equal to 0. Once we do that, you can see that the denominator, once we multiply both sides by the denominator, will disappear. So we have, for the first derivative, 20x equals 0, divide both sides by 20, and we get x equals 0 as a critical number. So now I'm going to start another inventory of critical numbers. we have x equals 0 as 1. And then we also have these vertical asymptotes here, x equals plus or minus 2. Those are going to help me set up my intervals. Okay, so now the second derivative, I need to check to see if we have any inflection points other than the vertical asymptotes that we were looking at. So if I set the second derivative equal to 0, again the denominator will disappear, and I'm left with the negative 20 times 3x squared plus 4 equals 0. Divide both sides by the negative 20, and that gives me 3x squared plus 4 equals 0. And now I subtract 4 from both sides. 3x squared equals negative 4. Divide both sides by 3, and we get x squared equals negative 4/3. Well, if I take the square root of both sides, I get an imaginary result here. So there are no inflection points other than the two vertical asymptotes. So just to keep track of what we were doing here, we did f prime here, and then this was the second derivative, f double prime. So that just helps me kind of keep track of what I was going on, because if I'm doing this during commercial breaks or something, I'll probably forget. So at this point, we've done everything we need to do. We just need to set up our intervals, which will be including any vertical asymptotes, critical numbers, inflection points that we might have. We don't have any inflection points, so they won't pop up in our intervals. So we start at negative infinity, and we're going to our first critical number, which is negative 2. And then from negative 2 to our next critical number of 0, and then from 0 to 2, and then from 2 to infinity. We're going to set up a big table here. Everything is going in this table. We need some test numbers. So we'll pick those out. We're going to plug into the first derivative, and we're going to plug into the second derivative. The first derivative will tell us increasing or decreasing. The second derivative will tell us concavity. And it's all being shown in this table. So within this interval, a good test number would be negative 3. For this interval, a good test number is negative 1. Here, positive 1. And finally, 3 here. Now we might also need to come up with a couple of more ordered pairs, just if we wanted to have a slightly more accurate graph. So now I'm going to take this negative 3 and plug it into the first derivative. This is going to tell me increasing or decreasing. So negative 3 goes in. Now what I notice in the denominator is that no matter what I get inside, I'm squaring it, which means I'm going to be positive. So the denominator for the first derivative is always positive. So now I just need to look at the numerator, decide if it's positive or negative. Remember, all we care about is signs. So this numerator becomes negative. Negative divided by positive is going to be negative, which means I'm decreasing. I'll just go right across for the first derivative. Take negative 1, plug it in. It's going to be the same result. Positive denominator, negative numerator. So I get negative, which means I'm still decreasing. Take 1 and plug it in. This is positive still. This is now positive, so I get positive, which means I'm increasing. And take the 3 and plug it in, we'll get the same result. Positive, so we are increasing. Now you could draw arrows down and up here if you wanted to, just to make sure you understand what the arrows mean when you do that. Okay, I take negative 3 and now I'm plugging it into the second derivative, so I'm looking at this line right here. Now I want to do the same kind of analysis. The denominator this time is to the third power, so I'm not going to be always positive or always negative. But the numerator has a square on that x, and then it's a positive 3 and a positive 4. So no matter what inside, I'm going to wind up positive. But that's a negative sign out front that I'm going to attach to that 20. So my numerator is always going to be negative this time. Instead of my denominator in the first derivative always being positive, the numerator is always negative, which is nice. It saves me a little bit of time. So we take the negative 3, plug it in. Squared is 9. Then 9 minus 4 is 5, which is positive. To the third power is still positive. So I have negative divided by positive, which means I'm negative, which means I'm concave down. Take the negative 1 and plug it in. Negative 1 squared would be 1. 1 minus 4 is negative. To the third power is still negative. Negative numerator divided by a negative denominator means that I'm positive, which means I'm concave up. Take 1 and plug it in. Again, the numerator is negative. 1 minus 4, 1 squared is 1. So 1 minus 4 is negative 3. Cubed is still negative. So negative divided by negative is positive. so we're concave up. And finally, 3. Numerator still negative. 3 squared is 9. 9 minus 4 is 5, which is positive. Cubed is positive, so we're still positive. And that means we're concave up. So we have everything that we need. We just need to talk about now what each of these means. Decreasing and concave down. The only way we can be decreasing and concave down is if the graph looks something like that. Decreasing but concave up, the only way that can be possible is if the graph looks like this. Increasing and concave up, the only way that's possible is if the graph looks like this. And then increasing and concave up. Sorry, this should not be up. Let me go back. We take 3 and plug it in. That's 9. 9 minus 4 is 5. Cubed is positive, but the numerator is negative. So this is actually concave down, and this is negative. Okay, so now increasing and concave down. The only way it can be increasing and concave down looks like that. So obviously I know what the graph is going to look like here, and that's how I caught that mistake. Okay, so now we have everything we need. We have a graph that looks like this in this region here. The only way that's possible with this horizontal asymptote right here and an x-intercept right here and a vertical asymptote sitting right here is if the graph does something like this. Remember, I'm not actually touching those asymptotes, I'm just coming very close to them. Likewise on this side, we have this sort of look to it. We have an x-intercept here, we have a horizontal asymptote here, vertical asymptote here. The only way this graph is going to make sense is if it does something like this. Okay, in between, we have a y-intercept here, and we have this sort of shape. We're switching from decreasing to increasing here, which means we have a relative minimum with this sort of shape. So basically what's going to happen here is the graph will look something like this, keeping in mind we can't cross those asymptotes. And that completes the graph. If you wanted to be a little bit more accurate, you could find a couple of more points. You could maybe put in -4 into the original function and +4 into the original function to get where this value actually is, so that you could have a slightly more accurate graph. And just comparing between these two sides, probably because of symmetry, we can say that they should be pretty much mirror images of each other, and obviously the way I've graphed that, that's not the case. So my graph is slightly off, but hopefully you understand that you can make it more accurate by just making a couple more ordered pairs. And once you've done that, then your graph will become much more accurate. For the second problem, we're basically doing exactly the same thing. We want to start off with vertical asymptotes, and you'll notice that we do have a vertical asymptote when x equals 2. Horizontal asymptotes, we don't have any because the numerator's degree is bigger than the denominator, but it's exactly 1 more than the degree of the denominator, so that means that we have a slant. And we need to figure out what the equation of the slant is. So to do that, we need to do long division, x minus 2, and then inside we have the numerator, x squared minus 2x plus 4. We don't have to make up any missing terms, so that's good. What times x gives me x squared? Well, the answer is x. So then you distribute. X times x is x squared. X times -2 is -2x. We draw our line, change all the signs, and add. This one disappears, and I'm left with just 4. There's nothing more to divide, so this is actually very easy to do. We wind up with 4 over x minus 2. So this is my new function now. F of x equals x plus 4 over x minus 2. Basically all we've done there is just made it into a mixed number. Instead of an improper fraction here, if you want to think of it that way, now it's a mixed number. Well, what happens as x goes to infinity is this takes over. So my slant asymptote is that part, y equals this linear part right here, x. So because of that, I can draw in that slant asymptote. I'll try to do that carefully. There is y equals x is my slant asymptote. And then I also have this vertical asymptote of x equals 2. So I'll draw that one in there. Okay, next part of my inventory, y-intercept. Set x equal to 0. This is gone, this is gone. I have a 4 in the numerator divided by -2 in the denominator. So I do have a y-intercept of 0, -2. So I can mark that. For x-intercepts, I set y equal to 0. So I have 0 equals x squared minus 2x plus 4 over x minus 2. The denominator goes away when I multiply it by both sides. Then I have x squared minus 2x plus 4 equals 0. So I want to factor that thing. Two numbers that multiply to give me 4, but I give me negative 2. There are no two numbers that do that, so I need to use quadratic formula. X equals negative b, so 2 plus or minus the square root of b squared, which is 4, minus 4 times a times c, so times 1 times 4, over 2 times a, which is just 2. So now inside the square root we have 4 minus 16. We get 2 plus or minus the square root of negative 12 over 2. This is imaginary, which means that there are no x-intercepts. So x-intercept, none. Okay, so this graph does not cross the x-axis. Now we need to set our two derivatives equal to 0. I've already given you the first and second derivative to save time, but if I needed to take the derivative of this by hand, I'd have to use the quotient rule. Same here for the first derivative, use the quotient rule to get the second derivative. So for f prime, we set it equal to 0. The denominator goes away. I can zero product property the numerator, and I get x equals 0, or x minus 4 equals 0, so therefore x equals 4. So I have two critical numbers. I'll start my inventory of critical numbers over here. I have the vertical asymptote for sure. I have x equals 0, x equals 4 as additional critical numbers. These critical numbers tell me when the slope is equal to 0. So f double prime, set it equal to 0. When I do that, the denominator disappears and I'm left with 8 equals 0, which means, since that's not true, we have no inflection. So let me write no in front of that. No inflection. Additional inflection points, not including that vertical asymptote. So these are the only critical numbers I need to address. So I set up my table of intervals. I have negative infinity to my first critical number, which is 0, then 0 to 2, then 2 to 4. And I need some test points, some test numbers. A good one here would be negative 1, and then 1, and then 3. First derivative, second derivative. Take negative 1, plug it into the first derivative. Notice that the denominator will be positive always. The numerator, negative 1 minus 4, is negative 5 times negative 1. So we have a negative times a negative, which is positive, divided by a positive. So the first derivative in this case is positive, which means we are increasing. Then we go into our second test number. So I plug 1 in, still positive here. 1 minus 4, though, is negative. So the numerator is negative. We are now negative, decreasing. And for the third one, still positive here. 3 minus 4 is negative. Times a positive. Negative times positive is negative. Negative divided by positive is negative, so we are decreasing. And I have one more interval to tack on here. 4 to infinity to finish this thing off. Need a test point here. We'll call it 5. Take 5 and plug it in. Denominator is still positive. 5 minus 4 is positive. This is positive. We are positive, so we are increasing. Second derivative, same numbers. The numerator is always positive. We are cubing, so we don't know that we're always positive. Negative 1 minus 2 is negative. To the third is negative, so we are negative, which means we are concave down. We have 1 plugged in. Positive divided by negative is negative, concave down. We have 3, plug it in. We get positive, so now we are positive, so concave up. And 5, plug it in. We are positive, so again we are concave up. So increasing and concave down means that we look like this. Decreasing and concave down means we look like that. Decreasing but concave up means we look like this. Increasing and concave up means we look like this. So with this number right here, the only way this can happen is if my graph does this. One thing I don't know is where my critical number is here. I did know that one because it's the y-intercept. This one I don't know, so I'm going to have to plug this in. 4 squared is 16. this becomes negative 8, so 16 minus 8 is 8. 8 plus 4 is 12, over 4 minus 2, which is 2. So we get an ordered pair here of 4 comma 6. So at 4 up to 6, there we go. Now I have an ordered pair, and I know that my graph is going to do something to this effect here without crossing that vertical asymptote. So that's how you do this one. I know it was very quick, but you can watch it again.